In this video, let's recap what we covered last week. We started with the definition of supervised learning. The goal of supervised learning is to learn a classification model from the labeled instances so as to predict the labels for unseen instances later on. The first phase, where we are learning a model, is called the training phase, and then the second phase is called an inference or testing phase. For the learning phase, we need instances and their class labels. So instances are typically denoted by a capital X and a bold X if it is a vector. And the label is kind of denoted by Y. And then and X kind of represents these set of attributes or features, and Y, a class label, is coming from a set of class labels capital Y. The assumption in supervised learning in general is that unseen instances follow the same distribution as the labeled instances. So any model that you train on the labeled instances could be used for unseen instances because they are coming from the same distribution. So the steps involve learning and inducing a model based on training data during the training phase, which means you need to answer these questions. What are the kind of model you want to learn? Is it a linear model? Is it a circle around the points, and so on? Can you learn such a model? Does your data have enough of variation to kind of be able to learn such a model? So for example, if it is linearly separable or not, which means can you actually learn a line that will separate the positive points from the negative points? And how do you set the parameters? For the testing phase, you are testing whether you're testing the model on unseen instances from the test data set to evaluate the model. If it is labeled, then you can evaluate based on those labels. Otherwise, you are just inferring the label using the model. So then the question there is, what is a good measure of evaluation? We talked about evaluation measures. We said that we could create a 2x2 confusion matrix or a contingency table where you would find out how many instances are there in true positive, false negative, and true negative. And then we can create a bunch of evaluation measures like accuracy, precision or positive predictive value, recall or sensitivity. A harmonic mean of precision and recall is called F1. And then in medical informatics community and so on, it's instead of precision and recall, it is common to report specificity and sensitivity, where sensitivity is the same as recall, but specificity is 1 minus the false positive rate. So it is on true negative divided by false positive plus true negative. We also saw what a receiver operating curve is, so ROC, receiver operating characteristic curve, and the fact that you could find out area under the curve to see which classifier is better when you're comparing two classifiers in the same data set. Again, to recall, the receiver operating characteristic curve is a plot of true positive rate on the y-axis and false positive rate on the x-axis. So it's basically sensitivity against 1 minus specificity. We went through a toy example data set on buying health insurance with 14 instances and 4 attributes: age, income, student, and health condition. And this was a binary classification task. So there were only 2 possible labels. And using this, we kind of derived some baseline measures, right? So if you have no learning then and you just use the majority class, then the accuracy would be 9/14, and the majority class itself would be yes class, and that would be 64.3% accurate. That again, just to kind of recall that the data set is instances your friends who bought or did not buy health insurance, and the task was who would buy health insurance based on these four factors. We looked at kind of always yes model and always no model, and we saw that always yes model was had an accuracy of 64.3, always no model was had accuracy of 5/4, that's around 36%. Okay, then we talked about a decision tree, where we said if we create a tree with age as the first node and split the data instances into three groups, we see that for if age is between 26 and 40, the label is always going to be yes. If it is less than 25, age is less than 25, there are 5 instances there and can be easily split using this question on whether they are student or not. So if they are not a student, then the label is no. If they are, then the label is yes. And on the other side, there are 5 instances with age greater than 40, and health condition is a good attribute to split on next, where again, if it is fair, the label is yes, and if it's excellent, the label is no. We could use this decision tree to label during the test phase or inference phase a data instance like this. Somebody with an age of less than 25, income is high, student is yes, health condition is fair, and we go down this tree and note that we land at a node on yes, and hence that would be your label. We could infer decision rules from decision trees. So if age is between 26 and 40, the label is yes. It has a support of 4/14. That means 4 instances out of 14 come down that path. And of all the instances that come down that path, all 4 of them have this rule to be true. So the confidence of the rule is 100%. Another instance would be age less than 25 and student no. The label is no. The support there is 3/14. So 3 of the instances come down that path, but for all of them that come that route, the confidence is 100%. Then we talked about nearest neighbor classifier. And in a nearest neighbor classifier, we are looking at density of instances and finding neighbors. In this case, if you're looking for 5 neighbors, then you really do not do anything during the training phase. It's called a lazy learner, but you just remember these instances. And then when a new instance comes in, you are going to find out who are the closest neighbors for this set. So there are 5 instances this way. You see that 4 of them are green, 1 of them is red. So the label for this instance would be green. That's class A. When you have another instance, you need to find 5 neighbors. So if you use the same circle, you may not find any instance. You may have to go far to get to the 5 instances. In this case, you're kind of expanding your neighborhood. Having a more relaxed similarity metric, and then you find that 3 of your 5 neighbors, closest neighbors, are red, that's class B, so the label would be class B.